join. And let's get started because there is lots to do. So last time we introduced the hidden Markov model as a model for doing part-of-speech tagging. And just as a reminder, with hidden Markov model tagger, our goal is to find the sequence of tags that's going to maximize the conditional probability of those tags with respect to the words we have seen. And I introduced the hidden Markov model as this kind of a weird process of generating data where you have this latent variables, namely part-of-speech tags, and given those part-of-speech tag, you are generating a word or emitting a word. However, what we are interested is the other way around. So what first step we did is to flip this conditional probability such that we can use the conditional probability of a word given a tag. And then at the end of our equations, we have came back to the first components of the hidden Markov model we introduced, namely the emission probabilities, the initial probabilities, and transition probabilities. So if we had the values for those probability, the next step would be to just plug them here and find a sequence of tags that maximizes these value. However, I have never told you what these values are exactly. I just said we need the concept of those values. So the next thing I want to talk about is how do we estimate those values. And we ended up last meeting by saying, okay, this is similar to N-gram language models. And for N-gram language models, we have used the frequency of, let's say, bigrams if we had used bigram language model. And actually, we are going to do something similar here too. Before I say that, I should mention that there are basically two ways you can go about finding these initial transition and emission and probabilities, and that's by using either supervised or unsupervised approach. And we, in this class, we are going to just talk about the supervised approach to tagging, meaning that we have a corpus where we have collection of texts, let's say sentences, and some annotators, some linguists have annotated each word with its grammatical role or part of speech in a given tag set. So now going back to what I was saying about frequencies, we have a labeled data set of sequences of words with sequences of tags. And let's say we have capital D of such labeled sequences. Our goal, as always, is to find these values, these parameters, which here are initial transition and emission probabilities, that are going to maximize the likelihood of seeing this training data, meaning the likelihood of seeing these sequences of words with these sequences of part-of-speech tags. And as always, if I have written here the probability of this data set, we would use the assumption that our data points are identically and independently distributed, which means that the joint probability of all of these labeled instances can be written as a product of their individual probabilities. I have a little bit of noise in my house. Does this distract you? If so, I can put my headphones on. No, all good. Okay, great. Because if I put headphones, I'm speaking too quietly, so I would rather not put them on. Perfect. So what I said is that maximizing the likelihood of a training data is the same as maximizing the product of individual probabilities. And here, in the next step, we have just plugged in the approximation of the probability we have introduced previously on this slide over here. Okay, so far so good. We are just plugging things in. And now there is a question of which values are actually maximizing this quantity over here. And the way we can go about this, which we will not derive, is to say, well, this is a function, and we know that the minimum of a function can be found where the derivative of this function equals to 0, right? So we would get a tree equation where we would calculate the derivative of this whole term with respect to pi A and B, giving us three different derivatives. We would then say these derivatives need to equal to 0, and then we will go about solving the set of these three equations, which we will not do here. And the reason we want do it here because it would require us to introduce a concept of Lagrangian multipliers to actually solve this optimization problem, which goes way beyond this course. But what you need to know is that if we had done all of that, what we would get as the estimation for pi A and B would actually be those frequency values, similarly as we have seen them for the n-gram language model. So the estimation is kind of simple. We are just counting things, but remember that the fact that the counts, the frequencies are a reasonable estimates for these probabilities would come from finding the solution to this optimization problem, which we haven't actually done. So it's not random that we have find that these values are good estimates of these probabilities. So what exactly are we then counting? For initial probability, we are going to add a special start token to each one of our sentences in our labeled corpus. And we are going to check for every possible tag in our tag set. Remember, we had over 30 of those in Pantry Bank. We would check how many times we go from a start token to a part of speech tag T. Divided by the number of instances in our label data. This is just to say how many times the first word in our instances in our data set are starting with a certain part of speech tag. Any questions? I have heard something, so just want to make sure that wasn't a question. Okay, good. Then to measure our transition probabilities, you just check from your labeled sequences for every possible pair of 30 tags. We check how many times we go from one specific tag to another given tag. So here from T to T prime, and we are going to divide this by number of times that this tag, the first one, occurs in the data. So relative to how many times it occurs, how many times it is followed by a tag T prime. And then for our emission probabilities, we are going to check how many times we see a certain word with a certain tag divided by the number of times that tag appears. So if we had, for example, part of speech tag noun, how many times a word, I don't know, dog is labeled as a noun relative to all the nouns in the corpus. Okay. And as we had an issue with n-gram language models where we had a lot of zero probabilities, this can be an issue here too. So your concept of smoothing can come into a play again. And just as a reminder, one way of doing smoothing is to add a little bit of probability to every single value here, such that none of them are zero, or take a little bit of probability mass from the things that have high probability and give it to the low probability items. And that's it. Now, once you have your labeled corpus and once you have calculated all of these values, now you are again in a ready to, and I wish I had, I have it here, perfect. You are ready to get your sequence of tags that maximizes the this probability, joint probability over here. Because now you do have values for your emission, initial, and transition probabilities. However, remember how last time we talked that this can be really slow? This is that toy example I given you where you have only 5 words. And you have a tag set that consists of only 2 possible tags, where in reality we may have more than 30 of them. And for this very simple case, we have seen that we have 16 possible sequences of tags, which means that for this very, very simple example, we would need to calculate this value for these 16 sequences. And this means that things are going to get slow once we have realistic sentence length and realistic tag set, the number of tags in our tag set. So although we can get exact, values we want just by plugging in all possible sequences, that's going to be very, very slow. So alternatively, we could try to something simpler, maybe. We could try out we can, instead of trying out every sequence, which has a runtime complexity of number of possible state to the power of sequence length, super slow, we can do something way simpler and try to predict the best tag given the previously chosen tag and observed words. So instead of checking all of these, pairs of tags and words and pairs of previous tags and a current tag, we are just going to simplify it by looking at the previous tag. And this is nice, but because the runtime is now only sequence length, at every position you are doing an independent judgment, more or less, but it's not going to be a very well-performed tagger because now we just simplify the whole thing way too much. And this brings us to another approach, which will have better runtime than this naive approach of running all of these sequences independently through this equation. So its runtime is going to be sequence length times number of possible states squared. And it's a dynamic programming algorithm which will just pre-compute some of these operations such that we don't need to recalculate them for every possible sequence of tags. Okay, so this algorithm is going to be called Viterbi algorithm. We are going to take advantage of the first order Markov assumption that we have said we are going to have in this hidden Markov model anyway. And we are going to use the fact that every observation is only influenced by the previous state, the next state, and the observation itself. And then we are going to develop a recursive algorithm out of it. Okay, so now I'm going to use Professor Vivek Srikumar's slides, and there is going to be a slight change in notation. He will use X, what I denoted, I used W to denote words, he uses X, and he uses I to denote tags, I use T to denote tags. So now we are going to switch to X and I. X are words, I's are the part of speech tag, which makes sense because usually we use X, Y for input outputs. All right, so now we are introducing that more efficient algorithm for inferring part of speech tags. I do want to stop here and emphasize that right now, what do we have? We have our formulation of a hidden Markov model. We said, all right, for a hidden Markov model, we need all these components, and then we had a bunch of components, most importantly, emission, transition, and initial probabilities. And then given those probabilities, we have defined the equation that we need to maximize with respect to the possible sequences of tags. And we need to plug those emission, transition, and initial probabilities into that equation. And these probabilities we have estimated by counting from the label corpus. Now, our current step, what we are doing is trying to make the inference faster, because we have seen that putting all possible sequences of tags and checking what kind of probability we get is going to be too slow because there are too many possibilities for which sequences we can put in. So now we are developing a dynamic programming algorithm to speed up our inference. This is what we are doing right now. Is there any question about that? Like, are you confused with where we are right now? I see no. I don't see we are confused. Okay, I feel like someone is about to speak, but
sorry, I just have one question. You explained, but I didn't follow very well. That how
Elham, unfortunately, your internet connection seems to be unstable, so maybe you can write it in the chat and I can come back to it when you finish writing it.
You're muted.
We can't hear you.
Oh yeah, Professor, you're supposed to be muted.
Okay, sorry, I don't know why I'm muted. So just a question from Elham. Is this the slide you are wondering about? Okay, and is there a particular step in this slide that's confusing or? It doesn't seem to be working. Okay, I will go over this one more time, just to be sure we are all on the same page. So we have our labeled data set, namely a sequence of words with sequence of tags. And our goal is to find a sequence of tags that we should use to label that sequence of words. So basically, if we write that, what I just said mathematically, we are looking at the sequence of tags that maximizes the conditional probability of sequence of tags given a sequence of words. However, the way that hidden Markov model is introduced, and you cannot change that, you're not Markov, you have no power to change what hidden Markov model is, and we are trying to apply hidden Markov model to a part of speech tagging problem, then you need to flip these conditional probabilities, because in hidden Markov model, we have this idea of these hidden observations emitting these things that we actually see. So things that we actually see are words, and our hidden things are part of speech tags. So this is why we have used Bayes' rule to flip the conditional probabilities. This part is irrelevant for the optimization, so we can ignore it, leaving only the thing above the fraction line as a part of the maximization process. And now here we have, unfortunately, this thing is going over the slide, but here in this step, let me turn on my laser point. In this step over here, we have used two assumptions we can have made. First, order Markov assumption and the output independence assumption. When you apply those assumptions to this equation, you will get this one. And in this last step, we just reintroduce the notation we have initially introduced. So here, nothing has changed except the fact that we have previously named this conditional probability to be this one. So we are just using that notation back. This is all that we have done in the last bit. And then these are the probabilities we have estimated by counting. So for every possible sequence of tags, you can plug in them to this equation to get their joint probability. And then you have as many of these probabilities as you have possible sequences of tags, and you can take the one which has the maximum probability as the predicted sequence of tags. That's how we go about this. And now with Viterbi, where we left off before this question, what is all about how do we make this process where we should put all the possible sequences of tags and then basically find the one that maximizes the value. How do we make that process faster? So here, this equation is the exact same equation we have seen in the slide I showed you before with the change of notation. Now X's are words and I's are part of speech tags. Everything else is exactly the same. Okay, so this is not going to be super trivial because, as you probably know, none of the dynamic programming algorithms are easy to grasp immediately. So bear with me. This is going to be a little bit, bumpy, but I think we can get there. So first thing from here that I'm going to do in the next slide is just write out this product in a more expanded way. So here in the red boxes, I have just highlighted. Imagine we have written this product out. and then just rearrange these two products. So here we have the probability of yn given it the previous tag. This comes from putting I equals n minus 1 in here, and this is the probability we get. And here, if we put I equals n, we will get probability of xn given in. And this is how these two terms are appearing here. So all we did here is expanded these two products and rearrange them such that the products that are connected to the same tags, namely tags appearing at the same position, are close to each other. Nothing special so far. Okay, here is just a reminder that probability of the y1 is the initial probability. Then emission probabilities are probabilities of words giving tags, and we have our transition probabilities, which is probability of moving from one tag into another tag. Okay. All right, so here now I need you to pay attention. So previously we have this maximization over tags y1 to yn. And now here we have maximization over y2, not y1, y2 to yn. And we have moved the maximization over y1 all over to the right side. So the reason why we can do that is because these factors over here are depending on y1. Ignore the fact that this one does not. So finding y1 that maximizes all of this is going to be the y1 we need, because all of these others do not depend on y1. So they are like constants. We don't need to consider them when looking for which tag should be the first one. Okay, so this is just a mathematical property of knowing if your function doesn't depend on something, that won't change the maximization with respect to the variable that we are looking for. And we have seen this a couple of times in this course already. So this is the first rearrangement we have done. And the next thing we are going to do is define score 1. Score 1 as an input to the scoring function, we can use any tag. So remember, in a part of speech tagging in Pantry Bank, we had 30-something tags. You can put each one of these 30-something tags independently to get score 1 for that tag. And it's defined as a probability of that tag times probability of seeing the first word given that tag. So this is just we are abstracting away the last two terms into something that we give a special name, score 1. And S is a symbol for any state. For us, states are the part of speech tags. So this is the first thing we do. This is our initial thing we need for our recursive algorithm. And then we are going to define the recurrence. Okay, so here, focus that we have a maximization over y2 over here. And the other terms that depend on y2 are the probability of the next tag given that current tag, probability of this current tag given the previous tag, and the probability of the current word given the current tag. So these are three terms that depend on y2. And if we had look at the rest of these products, you will see that there are always these three terms depending on, on the current tag. So we can define our recurrence to be score I for any given possible part of speech tag to be maximization over all possible previous tags given this value, where we have the probability of that tag given the previous tag, probability of a current word given that tag, and then here we can reuse that score of the previous step, so score of I minus 1 step. This is where the recurrence comes in. Okay, so right, so here I guess the visualization just shows you that this, how this becomes recursive. So here we have maximization over y1, and we also have here score 1, right? So here you see I minus 1, and then here is the I minus 1, where I minus 1 here is 1. And then for here we have maximization over y2. Okay, this is the I minus 1 is 2, and again I minus 2 comes here in score 2. So if we were keep doing this through this gigantic sequence of products of probabilities, we would keep seeing this kind of pattern. So that's good, because that means we can pre-compute some things and reuse them when we are trying to get the maximization of overall possible sequences. And let me then get into the final kind of overview of the algorithm. So in the Viterbi algorithm, we are going to have our initial step. So for each possible state, so for each possible part of speech, we are going to calculate score 1, which is going to be initial probability of seeing that tag times the probability of seeing the first word followed by that tag. So this is going to be, this is the abstraction, right? Here, S is abstract. It's a symbol that can serve for any tag. So if you were running this algorithm, you would have as many score 1s as there are tags, right? Don't be confused that there is just a single equation here. S should be S is any possible tag in the tag set. So you calculate score 1 for all possible tags. Now, your recurrence is that for I equals to 2 to n, for every possible state, you are going to calculate this value. And if it's not clear what are I going over, I goes over the sequence length. So we start from 1 to n being sequence length. So we start with a sequence of words. Remember, the goal is to give each word in a sequence a part of speech tag. So at every position in our sequence, we are going to calculate for every possible part of speech tag this value, which is we are going to find the maximum over what are all possible previous part of speech tag that maximize this value. All right, and at the final stage, we are going to find a tag that maximizes this value, and then you can recursively find which value had maximized previous one, and in this way you get your final sequence of tags. Why is this faster? So remember what was the runtime of our most naive approach, which is trying out all of the sequences and returning the one with the highest score. It was number of possible states. So for part of speech tagging in Pentry Bank, something like 30 something part of speech tags to the power of sequence length, and sequence length can be 100 words. So it becomes really, really, really slow. Here, when we go back to the algorithm, things are much better looking. So here we have this part going over all of the words in our sequence of words. So this is going to be resulting in a sequence of length times for every possible state. We have 30 something of those, let's say. But then for every possible state, we are also going to need to go over every possible state here to find this value for the previous state that maximizes this value. So we are going to have a quadratic complexity in the number of possible states. But this is way better than what we have seen with the naive approach. Okay, so that's it. That's Viterbi. It is a little bit funky to hear it for the first time for sure. I have sent you an email this morning, and I shared you an example of a Viterbi algorithm. I recommend that you check it out and that you see it through a concrete example where this sequence of steps will probably just be, click a little bit better than just hearing it for the first time here in the lecture. I know that these kinds of recursive algorithms are always, it takes a moment to truly get them. Okay, any questions about part-of-speech tagging, named entity recognition, hidden Markov model, Viterbi algorithm? Okay, so I want to wrap the named entity recognition and part-of-speech tagging by telling you how do you use these models. First of all, it is unlikely that the state-of-the-art hidden Markov model for, let's say, named entity recognition will be a hidden Markov model with manually designed features. Most likely, you will still have a neural network that predicts the BIO tag, entity tag for a given word. So hidden Markov model for us, I think it's important for you to know this algorithm, but if you now use an implementation, an existing one for the, let's say, named entity recognition, I just want to warn you that don't expect those to be hidden Markov models. Library you are going to use to get either part-of-speech tag or named entity recognition, unless you are working with a very special language, is most likely going to be spaCy. And there are two really nice examples to follow to see how to use spaCy for part-of-speech tagging and named entity recognition that I highly recommend that you check. So it's not surprising that these tutorials are a part of a book for cultural analytics. Remember, cultural analytics was doing text analysis to kind of learn something about people, about cultures through text. So maybe you are interested how certain character or existing, not fictional, but real person in history, how people have talked about them during time. There is useful to get a named entity recognition tool and see can you extract these named entities that are involved in this text. So yeah, I recommend that you check out. It's pretty simple to use spaCy. You just load it and then more or less you just need to apply it to your text. Let me see, can I find exactly where we have applied it here? Nope. Okay, so here it's as simple as that. So when you call document equals NLP text, what it does, it applies this NLP pipeline to your text. And with spaCy, that NLP pipeline, you have ability to sorry guys, let me go here. Okay, here. So with spaCy, you have option to specify what exactly you want to have in your NLP pipeline, but by default, it's going to evolve something like this, including your tagger, which means see, assigning part-of-speech tag and named entity recognition. So if you just call this pipeline to your text, you will get a bunch of things, including named entities. So yeah, just wanted to draw your attention to spaCy. It is a super useful tool if you are looking to use part-of-speech tagging or named entity recognition. Okay, any questions about spaCy? All right, so remember Hugging Face. Anytime you want to do something neural in NLP, Hugging Face is your immediate reaction, unless you want to use a closed model and APIs. And for doing this linguistic structure prediction, in your head, you should immediately think about spaCy if you are looking for a library to do something with those more traditional approaches to NLP.